Okay, this video is a review of all topics in quarter two for Advanced Algebra Trig 300. So it covers, the vast majority of what we're talking about here. Not everything, but 90% of the main topics. So let's look at this quick at the objectives here. We have polynomials, chapter 5, and we can see that right here. How to add and subtract them, how to break them down, longhand and synthetically, how to use the graphing calculator and understand end behaviors and so forth, and obviously how to solve when you set it equal to 0. Chapter 6, radicals and exponents, or rational exponents, we like to call it. Chapter 6, can you convert between forms? You understand extraneous solutions and understand the check form, rationalizing the denominator. Let's see what else we have here. Parent graphs, we'll see that in a graphing section, and then also function composition. That's kind of inputted into that chapter as well. And the last main chapter we talked about was logs, understanding exponential growth graphs. That's in our parent function, converting between log and exponential form in order to isolate the variable, and then solving in order to do that. Okay. So those are the main topics. Obviously, you can look at the individual videos on that, but let's go ahead and go through here. There's going to be a longer video, so you can hit the little tabs at the button to jump around as needed. But this pretty much is a good one-stop shop for most of the topics. All right, let's take a look here at exponents. What we're looking for here is understanding that we have a base, which is 2. The exponent is the raised number here, 4, and then the whole thing is 2 to the 4th power, which is 16. So that's the power. So let's take a look at this example down here. So the first thing I want to do is, I want to put a imaginary 1 exponent there. I want to distribute the cubic out here. So we have 2 to the 3rd power, which is 8. X to the 3rd power and y to the 3rd power. Then down here we have x to the 4th. Now notice it's a negative exponent, so I want to put it positive and put it on top. And a y to the 0 power is this 1. So right here is what we have. So now the last thing we can do is we can combine those bases. And when you multiply it, we have x to the 7th power, y to the 3rd power. So that's what we're looking for here. So over here we have all the different breakdowns of what we just went through in that one example. So when we're multiplying bases, we add exponents. So we're going to have x to the 5th. When we have a power to a power, that's when you multiply exponents. You get to the 6th power. Same thing here, you distribute. So that's going to be x cubed y to the 6th. So the 3 goes to both the x and the y. Here we have 2 minus 3, subtract exponents on division. So that's going to be x to negative 1. And then we see that what is x to negative 1? Well, it's a bunk bed problem, so we put it on the bottom and make it positive, x to the 1st power on the bottom. X to the 0 power is always equal to 1. That means there's no x's there, so we're just left with 1. Pickles to the 0 power is even 1. Okay. Here's an example where we distribute again. So we have x cubed over y to the 6th. And then down here, though, when I see this negative, one thing I like to do here is flip the whole problem. So this is going to be y squared on top, x on the bottom, and then I just make the exponent outside positive. Then I distribute. You don't have to do it this way, but that's why I always like to make them positive when I can. Okay, so going through understanding the properties of exponents is a big thing here. All right. Working with polynomials, okay? So a polynomial is again a larger number made up of smaller numbers. So that's 2 terms. Here's 3 terms. We would say that's a second degree polynomial. Second degree polynomials reduce both quadratics. So we're basically combining like terms. So the first thing I would do here is distribute at negative. So it's going to be negative 3x squared minus x plus 4. And then the last thing we do here is combine like terms. So we're going to have 2x squared minus 3x squared is negative x squared. Then we have 3x minus x is 2x. And then lastly, we have positive 4. So that's when you're just combining like terms. Okay. Now, this is, for a lot of people, I don't like to call it FOIL, but a lot of people are used to that, so that's a reminder for there. I call it double distribution, and over here we have like triple distribution. So term by term distribution is what we're talking about. So we're going to take the first term and multiply it by the front and the back. So we're going to have 40x squared minus 20x. Okay, and then I'll do a different color here. and we'll do 3 times both of those. So we'll have plus 24x. Now notice I lined up the like terms, they're both x terms, and we have minus 12. And then the last thing, this will look like a 12 there. Then we just combine them, add them up. We have 40x squared plus 4x minus 12. Okay, so again, you want to do each term, make sure you got a middle term there. That's the key, is that middle term, and that's what we want to have here. Same thing for here. So we're going to have term by term distribution, but now we have 3 terms in the back end. So again, I'm going to take the first term, multiply it 1, 2, 3 times. So we're going to have 6x cubed plus 2x squared minus 6x. Now I'm going to do the same with a different color for the back term, 7 times first, second, third term. So negative 21x squared. So I'm going to look for the x squared term here, minus 21x squared. Stack it up right there. Minus 7x, and then lastly plus 21. Okay, so I just did those 3 terms. Now we combine the terms here, and that's why I stack them, so it's easy to combine the like terms here. And notice I'm just adding them up as I see them. Okay, so here we have 1, 2, 3, 4 terms, and it is cubic because of the degree. Okay, so those are also terminology that we need to see as well. Okay, so understanding that. All right, so here is factoring. Okay, and we have different, factor completely with respect to real numbers, factor linearly, linear factors, I mean. So we're going to see those examples here in a little bit, but let's talk about the different ways that we see factoring. So here, always look for a greatest common factor. So here, what can I pull out of both the 4 and the 12? I can pull a 4 out, and as x squared and x, I can pull an x out. So when I factor that out, I'm left with 1x in the first term, and then a 3 in the second term. Okay, so that's what we're looking for there. Now here's grouping. So notice this is used when you have like 4 terms. This is what we usually see it as, or an even number of terms. And what we look for is, okay, we can divide the front and back. So what can I take out of the front here? I can take out an x squared. When I do that, I'm left with x minus 3. In the back, notice it's a negative, so I'm going to take out a negative 16, and you're also left with x minus 3, because if you take a negative 16 out of positive 48, you get negative 3. The key is those two are the same, so I'm going to factor that out. So we have x minus 3 as one of the factors, and the last one is x squared minus 16. Okay, and then we can say, okay, what can we do? Can we break that down a little bit more? Sure, we can. So the first is actually x minus 3. And then we can say, okay, this is difference of squares, and x minus 4, x plus 4. And we can see that here in our next example. Okay, difference of squares. So a squared minus b squared. This is where you have 2 terms, and they're separated by a minus, hence the word difference. So here we have, okay, so we have 2 terms, minus sign. So I'm going to start by setting up my parentheses, 1 negative, 1 positive, and then we take the square root of the front. 3x in the front, 3x in the front, and in the back. Now notice I put a 7 here because we can do it not only with this perfect squares, but what is the square root of 7? Square root of 7. So I did this on purpose, saying that if I ask for linear factors, we can break down anything as long as it's 2 terms separated by a minus sign. So it's a great example of difference of squares at a more advanced level. And the last thing we need to know is difference of cubes. So notice we have the cubic root, so we have the 3's here. Either a minus or a plus sign, and this is a pattern, so you have to memorize both of those. Okay, so let's look at this example. So when I see this is really 2x cubed minus 3 cubed. So there's your A and there's your B. So if I write this out, we're going to have 2x minus 3, and then we'll say, look at the back here. So we're going to do the minus 1 here. So we're going to square the first term, so it's going to be 4x squared. And then we're going to multiply both of them. I notice I'm going to use a plus there. 2 times 3 is 6x. And then another plus sign, and we square it back, which is 9. Okay, so that's the factored form there. Again, it's just a pattern that you have to memorize. All right, long division and synthetic division. So this shows you take any polynomial and break it down. So let's do long division first. So again, I'm going to write with x cubed plus 5x squared minus 7x plus 2. So I'm just setting it up here. And we're going to do x minus 2 here up front. So again, what I'm looking at here is the first term. How many times does x go into x cubed? Well, x squared times. Okay, now again, also I stack it up in that column. So that way when I get to the end, I know I'm done. So now you take this and you multiply it by everything in front. So I'm going to do x squared times x, which is x cubed. X squared times negative 2 is negative 2x squared. Now again, what we're going to do is we have to subtract all of that. Okay, so notice those cancel. 5 minus minus 2 is 7x squared minus 7x plus 2. Okay, let's do it again. So I'll do it in a different color. X goes into 7x squared, 7x times plus 7x. Notice I put it in the next column over. So again, multiply. So 7x squared and then negative 2 times 7x is minus 14x. Subtract all of that. Okay, I subtract it. So first terms cancel. Negative 7 plus 14 is 7x plus 2. Okay, bring down the 2. Notice I just bring down whatever is left over. And then let's do a different color once again. Let's go back to red. X goes into 7x 7 times. So 7 times negative 2 is negative 14. And 7x here. And again, we're going to subtract all that. So 2 minus minus 14 is 16. Now notice, that's x to the 0 power, that's x to the first power, so we can't divide. So this is a remainder, so it's always positive, and then you write down the remainder in the numerator, and then whatever you divide it by, the quotient down below, x minus 2. Okay, now we're going to do the exact same thing synthetically. Synthetic works, really for a lot of things, but we use it for linear factors, x to the first power. So when we do that, we look at the coefficients. So we have 1, 5, negative 7, and 2. And then what I'm going to do is I'm going to take the opposite, and that goes up here. So that's the linear factor. The solution is positive 2. So that's where it would cross like the x-axis. So again, when we do synthetic, we kind of copy down the first one, copy it down, and you multiply. 2 times 1 is 2. Add. Then you multiply. 2 times 7 is 14. Then you add, and you get 7. Then you add, you multiply to get 14, and then you add once again. Now notice it's the same coefficients as right here. So this is the remainder. This is x to the first power, or the 0 power, which is the number. This is x to the first, x squared. And notice we see it right here. So I translate it. That's x squared plus 7x plus 7 plus the remainder of 16 over x minus 2. And notice that is the exact same thing as what we have up here. Synthetic is a lot, quicker to use when we can. We use it for a lot of different reasons, which we'll see in this example. Well, let's look at graphing first, and then we'll show how it all comes together. So here we have graph and polynomials. So again, we use examples of John Travolta versus YMCA. So John Travolta again is, looking at opposite hands. So one goes up, one goes down, and this is for odd exponents. So x to the first power, x to the third power, x to the fifth power. So, what we see is like x to the third power could be goes up, down, and back up again. So if it's x to the third power, as an example, it crosses 1, 2, 3 times. Notice it has 2 turning points, because a turning point is always 1 less than the degree. And notice it goes, one hand up, one hand down. If I had, for instance, negative x cubed, okay, then we may have a pattern that looks like this. And again, it doesn't have to always cross. It can go down, up, and then down. And notice the hands are reversed. So here's an example where it goes up to the left-hand corner and down to the right. And here it crosses one time, and then would mean we'd have 2 imaginary solutions because it doesn't cross. So let's take a look. YMCA, the key here is they go in the same direction. So we have x squared is the most common example where we see a parabola. So let's look at x to the fourth power. So it might go down, up, down, and up again. So they both go in the same direction, and this would be an example of positive coefficient. But it crosses 1, 2, 3, 4 times, with 1, 2, 3 turning points. Now again, these are your local maximums and minimums, so you can use your graphing calculator to find those, so don't forget how to do that. And 4 solutions here, and go in the same direction. Again, if we had a negative, negative, I'll do it in a different color here, negative x squared, then the YMCA goes down, and here's an example of like 1, 2 solutions, okay, but it's going downward, so upside down YMCA. All right, so let's take a look at an example of putting this all together. So here we have a function, okay, notice it's 1, 2, 3 terms to the 4th degree, and what I want to do is factor it, graph it, break it down a lot of different ways. We're going to do everything with this. So let's first put it into a graphing calculator. So let's put this up and turn it on. Now notice I already put it in here, and there it is right there. And if I hit graph, it looks like a parabola, but this doesn't have the turning points, but it's an even function. Notice it's negative, so it's going down. We see 2 solutions on the x-axis, which means the other 2 are probably imaginary, because there's definitely going to be 4. So what I'm looking for on this graph is where does it appear to cross the x-axis at 1 and -1. So I want to test those solutions. So I'm going to do that synthetically. So let's set this up using synthetic division. So we have -1. And notice it goes from the 4th degree to the 2nd degree. So 3rd degree, there's none of them. 2nd degree, -3. 1st degree, none of them. And numbers by itself to the 0 degree, 4. So notice I have my placeholders in there. So now I'm going to use synthetic division. I'm going to start with 1. So again, copy it down, multiply, add, multiply, multiply, add, multiply, add. Now notice the key here is that it went to 0, which means it is a solution. So I'm going to go ahead and put that point on the graph. 1. Okay. Now let's go ahead from here. I'm going to break it down some more. I'm going to take out a -1. So let's do that. So -1, 1, add. I'm just quickly synthetically dividing it. And notice it goes to 0 again. So that means it's another solution. So I'm going to graph that point. I'll do it in this color. Okay. Now notice what's left. We have -x squared minus 4. So we're down to a quadratic, which means we can factor it. Okay. Now, if I factor that, I want to take out that negative in the front. So this is really -1 times x squared plus 4. So it's like the difference of squares, but it's positive, which means it's imaginary. So when I say factor completely, it's going to look like this. -1, and then we have the x squared plus 4. And then we also took out these 2 ones up here. So that's going to be, I'll do this -1 like that. So that's going to be x plus 1. And then the other factor was in red here, which was x minus 1. Notice I switched the signs there. So that's factored completely. Okay. Now if I say linear factors, we want to go ahead and break this down. So we have the -1 in front, and then this is x minus 2i, and then x plus 2i. Okay, so that's something we should remember how to do because it's difference of squares, but we added another negative, and that's where the I squared comes in. Okay, and then you still copy down the other 2 factors as they were. So linear factors means you should have 4. 1, 2, 3, 4 factors to match the 4th degree. And notice they're all x to the 1st power. Factor completely means using real numbers and no irrational numbers and so forth. Okay, so we see that here. So here's the 2 things. Another key point we should be able to pick up on is right here. If you plug the y-intercept in, plug 0 in, you get 0, 4. 1, 2, 3, 4. So that's another easy point. It's negative, so it's going down. And it's going to look like that, and we saw that on the graphing calculator. Okay, so that's a way to break down a polynomial. You should be able to use synthetic division to test points and so forth. Another thing I'm going to do is evaluate a point. So let's use synthetic division, and let's test, the point x equals 2. Okay, so where does it cross, x equals 2 over here? So, and again, I'm going to copy down. I'm just going to do it this bottom here. -1, 0, -3, 0, and 4. And since I'm testing 2, I'm going to synthetically divide -2. Or I'm sorry, I'm going to divide +2. Oh, got my wrong thing here. So, get my marker back here. Lost it for a second there. +2. Okay, so it's looking where it's going to cross when I input 2. So I'm going to do -1, -2, -4, -8, -11, 22. Oh, I messed up something here. Let's go back here a second. Because I know it's going to get a positive here, so I'm going to try this again. All right, so we got -1, -2, -4, there we go, -7, -14, and then we have -28, which is -24. Now notice it's going to be way off the graph. It's going to be way down here somewhere, and the point is going to be 2, -24. And what I'm looking for, this is like the remainder theorem. It should be a -24. Can't really see it there too well. And what we're looking for are these 2 points right here. Input, output, okay? And then 2, -24. And I'm going to rewrite that down here so it looks a little better. 2, -24, much better. And again, that's points way down here somewhere, okay? So that's another reason to use synthetic division. All right, now moving on to another topic, rational exponents. So this is radicals and exponents, and they're really the same thing. You can see the objectives up here in the upper right-hand corner. But let's kind of go through and simplify these, what we have here, okay? So, you know, we could show this as the square root of 4. That means really a index of 2. So this is really 4 to the 1/2 power. This is the cubic root, which is obviously 2. Then this one here, this is 27 to the 1/3 power. So again, the numerator is the exponent. The denominator is the index. Okay, so the index up front here, the root number, always goes in the bottom. So what number times itself 3 times is equal to 27? That would be 3. Okay. Look at this one here. This is 16 to the 1/4 power, which is 2. 2 times itself 4 times is equal to 16. Okay. Now let's take a look at this example here. So it's in exponential form. So we're going to put it in radical form. So we're going to do the bottom number is the index. So that means the square root. So you do put a 2 here. You don't have to because it's understood because it's the square root. And this is 16 and then cubed. I always like to break it down first. So what's the square root of 16? That'd be 4 and then you cube it, which is 64. Over here, notice it's negative. Okay. So we're going to have 1 over 32 to the 3/5 power. Okay, so we're going to have 1 over the 5th root of 32 cubed. So what's the 5th root of 32? 2. And then you got to cube it, which is 1 over 8. Okay, so that is our final evaluation of that right there. So just showing you quickly how to convert forms. Again, the bottom number is your index number, which goes up front, and then your top number is the exponent. You either make it bigger or you make it, either make it bigger or you make it smaller. It's always helpful to make it smaller first. All right, so here we have solving. So this is where we use the exponents and so forth to do that. So the first thing we're going to do is divide by 4. So we need to get this by itself. So we have x to the 5th is equal to 32. And I say, okay, how do we undo to the 5th power? Well, there's 2 ways you could write it. You could take the 5th root. Okay, so then the root and index cancel, and you have x is equal to, what's the 5th root of 32? 2. 2 to the 5th power is 32. Okay, the other way to show it is if you had x to the 5th equals 32, is to do it with exponents. So raise it to the 1/5 power, the reciprocal. And here we have 5 times 1/5, they cancel, and you get x. And what's the fifth root of 32? Again, 2. So you could do it in radical form, or you could do it in an exponential form in this case here, okay? But again, the key is to get the variable by itself. So the same thing here. So what I'm going to do is I'm going to use exponents here. So the 1/4 power, 1/4 power, okay? And we have x minus 3, because those cancel, equals 21 to the quarter power, okay? Now, what is quarter power? Now, it's hard to conceptualize that, so I'm going to convert it back to radicals. So we're going to have x minus 3. Now, notice here, this is an even index, okay? So when you do that, even means both positive and negative, because if I take a negative and do it times itself 4 times, you end up with a positive 21. So it's positive or negative. And the last thing we got to do is move the 3 over. So we have x is equal to 3 plus or minus the fourth root of 21. Okay, now again, that's a number. It's an ugly decimal that never ends. But notice the plus minus because of the even number. So I'm going to highlight that again to show even number. Okay, now over here we didn't have to do that because the fifth root, that's odd, which means keep the sign. Okay, keep the sign. Here it's even, so you need plus and minus. So I'm going to put that little note there. And don't forget that, the difference between the two, because that is definitely a big topic in this chapter. All right, so let's do a little bit more solving here. A couple examples. So now notice this one's an exponential form, so I'm just going to first get this by itself. So I'm going to move the 1 over. So we have x plus 2 to the 3/4 power is equal to 8. I'm going to raise both sides to the 4/3 power, the reciprocal, and do it to both sides. So now we have x plus 2, because notice these cancel, equals the cubic root of 8 to the 4th power. Now I just do that because a lot of times students like to see that because they can understand the radical part better. So what is the cubic root of 8? That's 2 raised to the 4th power. Now notice that's odd, so I just keep the sign. 2 raised to the 4th power is 16. So you have x plus 2 is equal to 16, and then move the 2 over, and you get 14. Okay, so pretty straightforward there, and no big deal. Now on this problem over here, notice we have a radical on one side, but not the other side. We need to get rid of the radical. So what I'm going to do is square both sides. Now notice when I square it, you square the entire side. A lot of students are going to want to put x squared plus 1 here. You can't do that. It's x squared, or sorry, it's x plus 1 times x plus 1. So if I show it off to the side, it's x plus 1, and we have to do that double term distribution, i.e. FOIL, a lot of students like to call it. So that's going to be x squared plus 2x plus 1 equals, and when you square a radical, it disappears. So notice we have no more radicals left over. We have a quadratic, which means I'm going to get everything on the same side. So I'm going to move this stuff over to that side. So 2 minus 7 is negative 5. And then we have negative 14 set equal to 0. This is chapter 4 material, so we, factor it in this case. And say, okay, two numbers that multiply to 14, that'd be 2 and 7. And we want to get a net difference of negative 7, or negative 5, so make that negative, make that positive. And there's your factor, and then x is equal to negative 2, comma 7. So we have two possible solutions, but we need to check for extraneous solutions, because since we raised it a degree, we have a piggyback answer. So what we need to do is plug those numbers in. So I'm going to plug in negative 2. So we have negative 2 plus 1. Does that equal the square root of negative 14 plus 15? I should say negative 14 there. Handwriting got a little slappy. Okay. So that's negative 2 plus 1 is negative 1. And that's the square root of 1. Now notice here, does negative 1 equal the square root of 1? Does negative 1 equal 1? No. So that means that negative 2 is not a solution. So let's go ahead and try 7. See if 7 works. So we're going to have 7 plus 1 is 8. Okay, so I'm just plug in 7 in here. And then we have 49 plus 15. If you add those together, you get 64. And does the square root of 64 equal 8? Well, yes, it does. So that is a viable solution. So notice we only have one solution. And there's no way to tell this at the beginning of the problem. You got to go through it. You got to check your answers on all of these solving with radicals and exponents. All right, function composition. So the whole purpose of this was to understand that, now like variables would be unknowns. Well, now variable, it could also be different variables, different letters could also be different functions, different equations. So we can see the three different things here. There's f function, g function, the j function. Okay, so the h function is combining the g function plus the j function. So I like to do it as, when I read this, let's go back to these here. I really see this as input squared minus 4. This is input plus 9, and I see that because I'm looking at the x here. That's my input. And this is negative 2 times input. So when I see this, they're inputting x. So this is the g function, which is x plus 9. And we're going to add that to the j function, which is over here, which is negative 2x. Okay, so here the new h function is adding these two together. So we just combine like terms. X plus negative 2x is negative x plus 9, and that's the simplified version of that. Okay, now over here this is like nesting function, so we're plugging a 2 into the f function and then plugging it into the g function. Okay, so let's assign these different colors. This one is red, blue, and we'll keep this one green over here. Okay, so when I see this, p of x, really this should be p of 2. So let's do p of 2 because we're inputting a 2, is equal to the g function, which I'm going to do in blue, is input. Let's get a different color here. Sorry. Input plus 9. And then we're going to plug in the f function, okay, which is in green. So that's right here. So that is going to be input squared minus 4. Okay, and what am I plugging in? It says right here we're plugging in a 2. So I'm going to plug it in for my input right there. Okay, so now we just go through and say, okay, if we evaluate 2 into the p function, is what it looks like. 2 squared, which is 4, minus 4, which is 0, and then plus 9, which is 9. Okay, so again, it's setting up and plugging one function into another function. Okay, so that's what we're trying to illustrate with function composition. All right, inverse functions. A couple things we gotta first do is, let's just go ahead and graph what this is. This is a parabola, and we'll do the inverse in red, or the actual function in red. So we're going to go up to 0, 2, and a stepping pattern is over 1, up 1, over 1, up 3, both left and right side. So for instance, this point here is negative 2, 1, 2, 3, 4, 5, 6. Negative 2, 6. Let's just get a couple points there. Now inverse, it means we're going to switch the x and the y. So notice the y-x line is right here. We're going to switch them. Okay, so we're going to first change that to a y. And then when we switch them, switch colors to show it, we're going to put the x in the y position and the y in the x position. Now again, we got to put it back in function notation. So we're going to move the 2 over. Should be negative 2. And then how do we undo the square? We take the square root. Now when we take the square root, imagine it's both positive and negative. So we have, the y squared and radical cancel each other. So we have plus and minus the square root of x minus 2. Okay, now that's a square root function. Okay, so that means we're going to have a starting point at 2, 0. And then my stepping pattern again is over 1, up 1, and then we go over 3, up 2. And then that's the positive side. So there's the positive square root, and then the negative square root is down below here. Okay, so it's not a function because it fails the vertical line test. But notice it's a mirror image across the inverse line right here. So this point right here is 0, 2. This point is 2, 0. Notice the x and the y switch. This point negative 2, 6 is 6, negative 2. Oops, sorry, that point should be down here. 6, negative 2. Let's draw that a little bit better here. Sorry, I got a little sloppy there. All right, so that point right there is 6, negative 2. And notice it's the exact same point as that there, just switched the x and the y value. Okay, so that's what we're doing there. Now, to verify it, we have to be able to plug one function to the other. So here we're plugging the inverse into the regular function. So the regular function is, you know, y. I'll put it with y equals so we can see the y part. Is input squared plus 2. And what we're going to do is plug in the inverse function, which is plus or minus the square root of x minus 2. Now notice what happens here is the square and the square root cancel each other out. So you're left with x minus 2. And then we have this plus 2 out here. And notice the 2's cancel out, and you're left with y is equal to x, which is the line that we want. Now we'd have to do it the other way too. We have to put the inverse on the outside, so we have plus or minus the square root of input minus 2. And then here we're going to plug in the function of x squared plus 2. Okay, so here notice what happens now. Put a y here. So we have y is equal to, now the positive 2 and a negative cancel. So now we have plus or minus the square root of x squared. The square and the radical cancel each other out, and you're left with y is equal to x. So since it works out both ways, they are inverses of each other. Okay, so we have to understand how the graphs work. We have to know how to verify it, and we have to know how to switch the letters and then isolate the y variable. Okay, so here's some parent functions. Let's scroll down a little bit. So here's the parent functions, the ones that we should know to date. Absolute value, which is a v. X squared, which is a parabola. The square root of x, which is a sideways parabola. Notice only half of it, the positive side. Cubic root of x. So we have, the sideways s here. X cubed, John Travolta. Okay, so it goes up and it goes through 0, 0. And then we have 1 over x. So, we didn't see a whole lot of this, but that is one of the parent functions that we're going to see a little bit more in the second semester. Okay. So these parent functions you definitely need to know. So let's take a look at some more examples with translations. Okay, or put it into a translation form. So here's again all different parent functions. We have first degree, which is the line. Second degree, which is a parabola. Cubic. John Travolta, we saw square root and cubic root. So just like the other, and absolute value down here. Now notice what I did was I put them all in translation form. So I put them all in parentheses raised to an exponent, or in this case down here, absolute value. And then we can see the shift. So we have the HK. We take the opposite of the inside of the parentheses and then comma K. So here we have a starting point. Notice the HK. So there's the vertex, the middle of the S. This is point slope form. So notice here's point slope form. And then the A value up front tells you the scale. So the three things that you want to be aware of is, number one, you want to know the parent function. Number two, you want to know the starting point, and that's the HK. And then 3 is the scale. Okay, let's erase that a little bit. That's a little cleaner here. Starting point, which is the scale. So for a line, it's the slope. For a parabola, it's the stepping pattern, and so forth. But notice the only thing that changes here is the degree. First degree, second degree, third degree. When you talk about square root functions, that's to exponent of 1/2. Cubic root, exponent of 1/3. So notice another good example of why we use exponents, because it puts it in the same form. We see the same thing with absolute value. So let's take a look at an example of a translation applied here. So when I see this here, this is a square root function. So again, I want to first identify what's the parent function. Well, this is a square root function, or x to the 1/2 power. So let's put it into this form right here. So we're going to have -2. Change that there. My pen's a little goofy here. -2. And then I'll put this in parentheses, x minus 3 to the 1/2 power plus 4. All right. Second, let's find a starting point. Okay. So the starting point in this case is going to be 3, 4. And we see that by taking the opposite here and then keep that the same. So we're going to go over to 3, 4. So that's my starting point. Okay. Now let's just graph the normal parent function of the square root of x, which is going to be, I'll do it in blue here. Okay. So we're going to be over 1, up 1. Square root means we go over 4, up 2. Okay. And this is from the last slide. Now, being that it's -2, we're going to flip it and multiply everything by -2. So we're going to go over 1, but down -2. We're going to go over 4, but not down 2, but down 4. So notice it's upside down and stretched vertically. So the scale is -2. It's being stretched vertically. Okay. So the red line here is the graph of this thing. So we have a starting point, we have a parent function, and we have a scale. So kind of going through graphing in those manners. All right, let's go on to the last major unit, which was logs. Now you have to remember, logs are exponents. So we should be able to convert forms here. So let's look at the different pieces. You always have a base, an exponent, and then a result, or which is the answer. So a log is log, and the base goes down here. The result comes next, and that's equivalent to the exponent. So when we see the example over here, this is really log base 2 of 32 is equal to 5. Notice the exponent is isolated. Here, if we're given a log form, let's put it into exponential form. So we have a base of 3 raised to the 4th power is equivalent to the result of 81. Okay. So let's take a look at like 4 kind of common things that come up in logs. Anytime you take a log of 1, that means 3 to the 0 power is equal to 1. And anytime you have a log of 1, it is always equal to 0, because anything to the 0 power is equal to 1. When we see this here, we're looking for, okay, I'm going to change this to log base 2. And what is 2? 2, 1/8, that is really 2 to the -3 power. Okay, so we're saying, okay, 2 to what power is equal to 2 to the -3 power? And that's going to be simply -3. Okay, so here notice it goes from switches positions. We're now in the denominator, which means it's negative, and then 2 cubed is equal to 8. So there's an example there. Now here we have, again, different bases. So I'm going to rewrite this as log base 3. I'm going to change 9 to 3 squared, and then we're multiplying it to the x power. So it'll be 2x. Okay. So now we're saying, okay, 3 raised to what power is equal to 3 raised to the 2x power? The bases cancel each other out, and you're left with 2x as your answer. Okay. When we see log with no base, it's understood to be base 10. So 10 to what power is equal to 100? 2. Okay, so notice in all these situations I'm trying to find a common base so the bases can cancel, and we're really just looking at the exponents. So it's a good way to do those problems. Now we also have change of base. And this is used like on calculators, where calculators a lot of times only understand base 10 numbers. But let's say you have a different base. So let's take a look at this example. So all we're going to do is take the log base 10 of the result, which is 13, and you're going to divide it by the base number. I'll do it in a different color, and 5 there. So I'm going to do log base 10 of 5. And you type that into the calculator, and you get the equivalent. So again, you just type it in the calculator, and it'll give you an approximate decimal of what that is. So that's a shorthand way to convert the bases on your calculator. Now let's take a look at expanding and condensing logs. The thing is, go back to the exponent section, and let's take a look here real quick. I'll just pull it up here to exponent section if I can find it. Right here. Okay, so notice everything we can do with exponents we can do with logs. If we multiply in bases, we're adding exponents. If we're a power to a power, then we multiply exponents. So let's take that same idea and let's apply it to logs, which we see right here. If we have a positive logs that were being added together, that means we're multiplying bases. If we have a negative log, that's like a negative exponent and goes in the denominator. So this is really, m in the numerator, and this is n in the denominator. Okay, so that's what we're looking for here. So when I have a positive log m, this is the same thing as log, and it's positive, so the m goes in the numerator, and it's a negative log n, so the n goes in the denominator. So how do we combine those two? Just like that. When we see an x out here, we can also, that means power to a power, so that means multiplying exponents. So this is really x out front and then log of m. Okay, so both of those can be in both positions. So let's take a look at two examples to show how this comes together. So in this case, we want to expand. So the first thing I'm going to do is, if this is in the numerator, it's positive. If it's in the denominator, it's negative. So I'm going to do log base 3 of the square root of x, and then minus, because it's the denominator, log base 3 of y cubed. Okay. Now, the next thing I want to do is convert this. So this is really log base 3, and what's the square root of x? That's x to the 1/2 power. Okay. So, and this part I'm just going to leave alone. Now, the last part is I want to get log of a single item. So we have this exponent out front. So I'm going to take this exponent and put it out front. So the 1/2 goes out front, log base 3 of x. Now we're taking log of a single item. So we know we're done there. Put the 3 out front, log base 3 of y. Okay. So notice we expanded it. We're only taking a log of a single item. The exponents are up front, and everything's separated, numerators and denominators. Now, the exact opposite here is, what if we want to condense it? So I'm going to look, what's positive and what's negative. So the first thing I'm going to do is check, or do we have the same base for everything? This only works if we have the same base, log base 3. So now we're going to make a large fraction. Anything that's positive, we'll put in the numerator. So we have a positive log here, so 4 goes up here. We have a positive here, so the y goes up here. Okay, and then we have a negative down here, so I'll do that in a different color, so we can see the negative right here. So that means that x goes down below. Okay, so very simply combine, and we do this because now we're able to convert forms if we need to do that, because we have it all into one log. All right, so let's take a look at solving. And a couple different things to do. One is to get a common base if you can. And the other thing is, if the unknown or variable is stuck in a position you can't isolate it, then that's when you have to change forms. So let's first look here. First thing I'm going to do is look, okay, how is 9 and 27 related? Well, they're both base 3 numbers. So this is 3 squared, and this is 3 cubed. So then we say, okay, let's raise it to the 2x power. Let's raise this one to the x minus 1 power. Well, power to power means you just multiply. So since the bases are the same and the equation is equal to each other, that means the exponents have to be the same. So here we're just going to do 2 times 2x is 4x. Set the exponents equal to each other. And then 3 times x minus 1 is 3x minus 3. And then we just have a simple linear equation, but we're dealing in the exponent position. And we could do this because the bases are the same. So this is simply x is equal to negative 3. Okay, this basic algebra. Now we're going to do the same thing over here. This is 3 to the x minus 1, and this is 3 to the 4th power. So since I have the bases the same, then I can just set the exponents equal to each other, and presto. Okay, x equals 5. Now that doesn't always work, because sometimes the bases are not the same here. So let's look here and see, are the bases the same or not? So a lot of people say, well, they're not, but really they are. This is really 2 squared, and then 1/2 is 2 to the negative 1st power. And then now we have both base 2. So this is raised to the x power, and this is raised to the x minus 3 power. So since the bases are the same, we can set the exponents equal to each other. So here I multiply the exponents, and here -1 times x minus 3, which is -x plus 3. Okay, so here we have 3x is equal to 3, x is equal to 1. Okay, so notice that works always the case here. Now notice in here, the exponent is stuck in the log position. So before we get to that, let me just go back to this problem right here. Let's move this down, and let's write this in a different way. So I'm going to do this and say, okay, sometimes the exponent is stuck here. And we lucked out because 81 is a base 3 number. But if it wasn't, how else would you solve this? Well, since the exponent is where the variable's at, we have to isolate. So I'm going to change forms. So this is log base 3 of 81 is equal to, and then the exponent goes over here. And then we say, okay, what's log base 3 of 81? That's 4. 3 to the 4th power is 81. And then we say, okay, now we just break it down to here, and notice it looks a lot like this. So x is equal to 5. So that's another way to solve that problem. Okay. Now, this one here, we're in log form, so we're going to have to combine it, condense it, and then convert to exponential form. So the first thing to do is put the 2 in the exponent position. And then we're going to put this in the numerator and that in the denominator. They're both at the same base, so I'm going to do log base 2. And the numerator is x squared. And the denominator is 3. And I know positive log, negative log. And this is equal to 4. Now that we have a single log, we can convert forms. So this is 2 to the 4th power. 2 to the 4th power is equal to x squared divided by 3. Okay. So now we say, okay, no big deal. This is a cross multiply problem. So that's 16 is equal to x squared divided by 3. Multiply 16 times 3. Get rid of that 3 in the bottom. And last thing here is take the square root. Okay. So then we remember we take the square root. We have plus minus both answers of 8. Okay. So there's a great example of condensing logs and then changing to exponential form, and we did that to get the x out of the log. Okay, and that was the whole purpose there. All right, so that kind of wraps up quarter 2 main topics. Again, I know this is a longer one, but you can jump through it using the buttons in YouTube. And again, if you want to follow up more explanation, go to that specific video, and that should help you out.